Okay, can you hear me?
Yes, we can hear you.
Okay, so I already thanked the organizers, but I think like I'm really grateful to them for like really wonderful organization. I know it takes huge amount of effort. So thank you, John, thank you, Mushin, and thank you, Karen. So and thank you all the students. So as I was, let's restart and hopefully like this time there will be no glitches. The way I have structured this these lectures are to in three parts. Basically, like I'm going to start with a very brief overview of very important two developments which happened 60 years ago, and they were concerning the genericness of singularities in GR and the discovery of cosmic microwave background. I'm focusing on these two because these two are the one which have played a very important role also in the evolution of loop quantum physics of loop quantum cosmology, basically singularity resolution in loop quantum cosmology, and the effects which we want to see in the cosmic microwave background. This will be very brief overview, like uh, just for the historical purposes for young students. Then I will be going to part A, which will be an overview of singularity resolution in loop quantum cosmology. Again, like this part is very mathematical, but I'll be skipping most of the details and just focusing on the main results. And I apologize if I miss some important references or some important results. Part B will be concerned with trying to introduce how do we do Hamiltonian framework for cosmological perturbations, basically using Langlois' pioneering work, which have been used in the two main approaches to loop quantum cosmology in the last 10 years, and giving the glimpse of, in practice, how do we explore quantum geometric effects in CMB. The goal of part A is to give an overview of the progress on singularity resolution, and the goal of part B is to tell young students that irrespective of whether they are doing loop quantum cosmology or any other approach to quantum cosmology, how can we use the lessons we have learned in loop quantum cosmology to capture the effects in CMB. I have 83 slides. I probably was too ambitious in this. I realize probably they cannot be covered in 2 hours. So I request Jurek to tell me in advance like when the break is going to come, and then I will try to reshuffle some things and see like whatever we can cover.
Yes.
Okay, so let's look at this picture, which tells us about the almost complete history of our universe. We live here somewhere 14 billion years ago, and astronomers tell us that we are passing through a period of dark energy. And GR, along with particle physics, has been extremely successful in telling us from the very first beginnings of the universe, which are at the grand unification scales or sometime afterwards. We still have a lot of desert here of theory, which we still have to uncover. But from those scales about from electroweak transition up till now, we have tremendous knowledge about the history of our universe, thanks to many precise experiments, both in particle physics as well as in astronomy, like in CMB. And let's not forget that GR has been tested to great scales using LIGO and advanced LIGO. And the upcoming experiments in gravitational waves are going to constrain many more models based on GR and modified gravity. Perhaps one of the biggest discoveries which is tied to CMB is that now the the astronomy experiments are so precise that we can even rule out various favorite inflationary models. I won't be covering this at all in my talk. Later on in the conference, probably there will be some talks based on that. So the main question mark in this picture is this quantum gravity wall. And that's where most of us who are doing loop quantum gravity or spin forms or other approaches to quantum gravity are most interested in the cosmological aspect. We want to understand what is the physics of this. And for that, we want to understand how to build those models mathematically, reliably, free of ambiguities and so on, like the physics. How can we uncover that? And the talk today will try to give you a glimpse of that. There is a lot of work which still needs to be done. And I'm very hopeful that many of you in the audience, the young students, will be able to finish this task. Okay, so with this very brief introduction, let's go back almost 100 years. In the late 20s, when Edwin Hubble discovered one of the most phenomenal discoveries of that time, that the galaxies are moving farther from each other. What Edwin Hubble actually discovered was that fainter the galaxy, the faster it recedes. And this came as a big shock at that time to both the theoretical and observational community of physics, which The way most of the physicists used to believe that the universe is static or infinite and it has no age. And we do not know how, like we didn't had any problems of Big Bang and so on. Once Hubble discovered this, Friedman and Lemaitre, they worked very hard to find a solution in general relativity, which was already tested through the solar eclipse experiments of Eddington, that there was a solution in GR which explained the expansion of the universe. And one of the features of Lemaitre's model was a primeval atom, some sort of a seed of the universe, which was in the very early times from where all of the universe originated. So Lemaitre's discovery and Friedman and Lemaitre's model, they led to many, many questions. That if one accepted the expansion of the universe, and one of the main questions was how did the universe begin, and how do the galaxies form? So we won't be concerned with how do the galaxies form. That's where most of the theoretical astrophysics or astrophysics communities work on, or cosmologists work on. Our concern is how did the universe begin? And this problem cannot be answered apart from asking what is the problem of initial singularity? Because once you accept that the universe has been expanding and you run that backward in time, the universe must have started from some some point, and that point, Friedman and Lemaitre and also Tolman had later found that that's the problem of initial singularity, where the equations of Einstein field theory will break down. Now, at that time, GR was a very well, like, astonishing theory, and Eddington, who was one of the forefront leaders of that theory, he believed that there is nothing wrong with GR and there is no initial singularity. He believed in the universe which was without initial singularity, and there are lots of philosophical arguments at that time, like why some people thought in that way. And Eddington at that time also believed that the singularity which is in the Friedman and Lemaitre and Tolman's models, they are artifact of the simplifying assumptions of isotropy and homogeneity. It was also believed that perhaps if you introduce an isotropy or if you introduce inhomogeneities, then the singularities will disappear. In fact, like I will just quote from Eddington when he says that philosophically, the notion of a beginning of the present order of nature, which means the existence of this initial singularity, is repugnant to me. I should like to find a genuine loophole. And Eddington either was trying to find the loophole or was trying to tell the community that there is no need to look at this issue right now. We can, because this is just probably coming under certain artifacts of assumption. And Eddington's ideas at that time, they greatly influenced Fred Hoyle, who was a very young physicist at that time. And Fred Hoyle later pioneered the steady state theory, which was based on the perfect cosmological principle, in which the universe looked not only same in space uniformly, but also in time. And in the steady state theory, there was no initial singularity. Recently, it has been found that the Hoyle and Bondi and and uh, and Burbage and Narlikar steady state theory, like those who worked on quasi steady state. Even Einstein was working on a very similar theory, but he didn't publish it, and there were some unfinished calculations which were found recently in Einstein's archives. Okay, so the steady state theory was essentially like the main developing theory at that time, and it was something on the lines of what was being talked about before Friedman and Lemaitre discovered the expanding universe. But at the same time, following Lemaitre's ideas, George Gamow was developing how from the ultra-dense state of matter, this Lemaitre's primeval seed, how can the elements originate and how will the expanding universe actually look like? And he predicted from his model that the universe will have a very cold background radiation if the universe actually started from this Lemaitre's primeval seed or something and was expanding as Hubble has discovered. In fact, the word Big Bang, which we will hear again and again in this talk, in this lecture, and probably also next week, that was coined by his arch rival, Fred Hoyle, in one of the BBC interviews in April 1949. I'm not sure whether you can see this, but Fred Hoyle was giving this interview, and he mentioned that these theories, which were based on the hypothesis that all the matter in the universe was created in one Big Bang at a particular time in the remote past, and then he says that it turns out that all of such theories are in conflict with the observational requirements. So it was actually Fred Hoyle who gave this word, and George Gamow was the principal father of the standard model of cosmology. So few years down the line, there was a divergence of the now I will show you two diverging slides, but they are actually like coming from the two sides. What happened was that in 1950s, Rai Chaudhuri essentially proved Eddington's assumptions wrong because he showed that the existence of singularities is there even if we relax the isotropy assumption. Even if you have an isotropic space-time, you can have singularities. And one of the fundamental achievements of Rai-Chaudhuri's work was this Rai-Chaudhuri equation, which plays a very important role in telling us when is the gravity actually attractive, plays a very important role in singularity theorems. These, these discoveries were in some sense catalyst for the work of Garrosh, Penrose, and Hawking in 1960s, in which they showed that the singularities are generic in GR. Even if you have anisotropies, even if you have inhomogeneities, you cannot get over singularities. And in fact, you have to violate the null energy condition to avoid singularities. What is a null energy condition? If rho denotes the energy density of matter or perfect fluid, and pressure denotes energy density of matter, then rho plus P has to be greater than or equal to 0. So I come from a tradition where matter means all matter, not just dust. So if I use the word matter, it would refer to all kinds of perfect fluid, not only just dust. So rho plus P had to be greater than or equal to 0. And we know like the radiation, dust, even inflaton do not violate null energy condition. Therefore, all of them will have singular spacetime. So this was the fundamental discovery in 60s from the theoretical side, where Eddington was essentially proved wrong that the singularities are inevitable in GR. But something very amazing happened at the same time from the observational side, and this came from geopolitics, and this was an amazing discovery, and which I think like students would love to think about and know about. Like in broadly in 1945, Arthur Clarke was conceptualizing the ideas of communication satellites when the World War II was ending. And based on that idea, both the Soviet Union and the Americans, they were working on how can we have these better systems for communication, and Soviets launched Sputnik 1 in 1957. And in reaction to that in 1958, immediately after that, like Americans started working deeply on the space projects, and the NASA was born. And in 1959, there was a NASA mission, which is called a Project Echo, in which they sent these balloon satellites, which were floating in the upper atmosphere, and then they will communicate with big horn antennas, which you see in the back of these two guys, to communicate across the Earth. Penzias and Wilson, who are shown here, they were trying to figure out how to make these communications much more accurate and precise. And they were not able to understand one very mysterious noise, which was not going away even after like taking care of everything, including the bird droppings on these horn antennas. It turned out that that noise was actually coming from outside our galaxy and was nothing else than the cosmic microwave background. So this was just one good side effect of the geopolitical race between Soviet Union and US at that time. The discovery of CMB, and this map is essentially one of the most modern maps which we have of CMB, in which these colored, the red, orange, and the blue colors, they tell you about the temperature fluctuations. So with the discovery of singularities and CMB, now we move towards the second part of my talk. We have seen that these two are fundamental things, and these two fundamental things which we want to build on. It's inevitable now, like that the people realized at the late 60s that the universe was indeed expanding. There was a problem of singularity, and we have to live with this problem and resolve it. People started working on how to quantize GR, and that led to many fundamental questions. And I'm skipping a large part of history between 1960s to almost like 20 years ago. And some of those fundamental questions which were asked by Wheeler and other people, that is our universe described by a classical continuum spacetime at all scales? Or what is the quantum nature of spacetime if we quantize gravity? If the spacetime has an atomic structure, as some people believe, then what is the fate of the Big Bang? And also, can that knowledge tell us how to go beyond the black hole singularities? How does a quantum spacetime affect the physics of very early universe? How does the quantum nature of spacetime affect the interior of black holes? And finally, does the quantum spacetime leave any signatures in the physics of very early universe, especially in the cosmic microwave background? So these are the fundamental questions which I have rephrased, which have been asked from last 40, 50 years in different disguises by different theoreticians. And these are the questions on which most of the loop quantum cosmology practitioners try to focus on, one question or the other. And I will try to give you the glimpse of some of the answers which are to these questions. Okay, so I hope there were no questions on the very first beginning of the talk, which was just a historical snapshot. Let's go to part A.
Yes, let's continue.
Okay, so the part A will be an overview of singularity resolution in LQC, and I have shown you all the pretty pictures, and those were the only pretty pictures I have in the talk, and the talk will now become slightly more denser towards the mathematical aspects, and part B is going to be even much more denser. So now it will be more and more denser in material, and let us see how much we can cover. So I'm listing some useful references for part A. I think it's impossible to list all the references because they won't fit the slides, and I'm just picking up some references which have certainly my prejudice involved here. I think like it's very important to recognize that one of the most fundamental works in the very beginning was this beautiful paper by Osteker, Boyewald, and Jurek Lewandowski, which laid down the backbone of mathematical structure of loop quantum cosmology. Then this paper, which is called the APS paper or the improved dynamics or the mu bar scheme, this is also useful references. This status report is a useful reference for all the mathematical aspects and also physical aspects. And these two reviews are also useful references for the students. Okay, so what is the motivation? The motivation is that we have a symmetry-reduced spacetime, as in loop quantum cosmology, which include like cosmological spacetime, anisotropic spacetimes, as well as black hole interiors. These provide a tractable and non-trivial rich ground to implement techniques of loop quantum gravity. Loop quantum cosmology is in a way a kindergarten to learn valuable lessons of loop quantum gravity and to gain insights on the physics of the Planck scale. And what can we learn in this quantum gravity playground? We can learn how to do a rigorous quantization in a self-consistent way, which means that we can learn how to figure out the physical Hilbert space and the observables. We can rigorously develop and test different tools and techniques to extract reliable physics. And also, like the experience shows that we can bridge out to numerical relativity, like numerical relativists themselves have played very important role in development of numerical techniques of loop quantum cosmology. We can also figure out, once we have developed such models, how to rule out different quantizations using internal consistency and finding their phenomenology and physical predictions. And we can understand the potential quantum gravity implications for the early universe, as well as understand and gain insights on fundamental issues like consistent quantum probabilities of the universe, or even like the lessons of loop quantum cosmology have been very useful to understand black hole information loss, in which Abe Ashtekar has done a lot of seminal work. Okay, now the main caveat, there are various caveats, but the main caveat is this. The quantization of homogeneous spacetimes, on which I'm focusing on, is like doing quantum mechanics of spacetimes. Whereas a full quantum gravity, like loop quantum gravity, is something like QFT of spacetime. I'm going to assume homogeneity of spacetime throughout. And because of that, various hurdles of quantum gravity, they can be bypassed. It does not mean that all of what I'm going to discuss is going to be true. Perhaps it has some glimpse of truth. The hope is that there are some qualitative aspects which can be captured. And the second main caveat, which I have not listed, is the loop quantum cosmology has not yet been derived from loop quantum gravity. So we still have to find the cosmological sector of loop quantum gravity. And we don't know like whether loop quantum cosmology is a standalone model in itself, or it still captures truth from loop quantum gravity. Okay, with these caveats, let's look at this slide, which is cosmology with some preliminaries. And I'll be slightly quick here, but like these slides will be there like just to capture like some of the details which we need. So next few slides will be on the cosmological preliminary. We are going to work with the spatially flat, homogeneous, and isotropic Friedmann-Lemaitre-Robertson-Walker spacetime, which has a metric which is given by this. I'm going to take mostly laps equal to 1 in this lecture. A of t is the scale factor. And we are going to consider perfect fluids, which are described by this equation 2. Rho will denote the energy density, P will denote the pressure, and u mu is the velocity relative to the co-moving observer. The energy density rho and pressure P, where pressure P can be written as minus of del by del V of Hm, where Hm denotes the matter Hamiltonian. They satisfy the conservation law, rho dot plus 3h, rho plus P equal to 0, which comes from this covariant derivative of T mu nu. H is the Hubble rate, which is A dot divided by A, the rate of change of scale factor divided by A. If you take a fixed equation of state, W, which is pressure divided by rho, then from this conservation law, it follows that energy density is proportional to scale factor to the power minus 3 times 1 plus W. If you have a pressureless test, then equation of state is 0 because pressure is 0, and energy density goes as A to the power minus 3. If you have relativistic matter or radiation, energy density goes as A to the power minus 4. If you have stiff matter or a massless scalar field, energy density goes as A to the power minus 6. If you have dark energy, which has almost constant like energy density with respect to matter, energy density goes as A to the power 0 plus minus some epsilon, depending on which dark energy model you're looking at. And equation of state goes as minus 1. If you have a perfect cosmological constant or dark energy equal to minus 1, then rho is a constant in terms of lambda and W is minus 1. I'm talking about these things because some of this jargon of cosmology we are going to use later on. The important thing is this is the metric, this is the conservation law. The dust behaves as A to the power minus 3, stiff matter behaves as A to the power minus 6. Now from the Einstein field equations, which is G mu nu equal to 8 pi G T mu nu, we can first obtain the Friedmann equation from G naught naught piece, which is Hubble square equal to A dot square by A square is 8 pi G by 3 rho. And the Raychaudhuri equation from the other pieces of the G mu nu equal to T mu nu, which goes as A double dot by A equal to minus 4 pi G by 3 rho plus 3p. Gravity is attractive. We can find from this equation when rho plus 3p is greater than 0. This is also the strong energy condition, which we'll refer to sometimes. And from A double dot equation and the Hubble square equation, we can find out an invariant, which is a Ricci scalar, which is kinematically given by this, and it is given by 8 pi G rho minus 3p. Now you can integrate these equations along with the conservation law, and one finds that if you don't have equation of state equal to minus 1, then A goes as T to the power 2 by 3, 1 plus W. And if you have cosmological constant, which is W equal to minus 1, then A goes as A is proportional to E to the power some square root of lambda T, where lambda is a cosmological constant. I'm missing out some cofactors here because I could not fit them into the equation here. Now, when A goes to 0, that is where the Big Bang is. I'm sorry, this has to be infinite. Rho goes to infinity in finite time. I'm sorry about this big typo. Rho goes to infinity in finite time, and Big Bang is reached. But the Big Bang is not the only kind of cosmological singularity. A quick look, there can be other kinds of singularities which come from choosing different equations of state. First of all, Big Bang has a dual, which is called a big crunch, which happens when you have a closed universe, k equal to 1 universe, or a big crunch is a future twin of the Big Bang, in which both the energy density pressure and the Ricci scalar will diverge. When A goes to 0 in finite time, the null energy condition is always satisfied, and this is what we will later see as a strong singularity. Similarly, there can be other singularities, and I won't spend much time on that. They are the big rip singularity, in which the scale factor actually goes to infinity instead of going to 0. There can be also sudden singularity, in which the scale factor actually takes a finite value, and even then the energy density and the Ricci scalar diverge. And then there can be other singularities like type 3 and type 4 singularities, which again happen at finite scale factors, but sometimes the energy density diverges, and sometimes even the energy density or pressure does not diverge, but only curvature derivatives diverge. So the important thing to remember is that in cosmological models, since we have this ambiguity with dark energy, cosmologists in the last 20 years have come up with various equations of state, which actually lead to various other kinds of singularities. And in quantum gravity, our goal is not only to just understand the resolution of Big Bang and Big Crunch singularities, but also other types of singularities. Okay, but we will come back to this at later time. Another thing which we will need later on is to understand some of the problems of cosmological models. Like, why do we even want to go beyond standard model of cosmology? And for that, it's important to understand what is a horizon problem. And I'm skipping like some various other problems of standard cosmological model. I'm just focusing on what we really need as a bare bones. For that, we should have, I want to first introduce what is a particle horizon. The particle horizon is a maximum co-moving distance the light can travel in a given amount of time. And if you have a fixed equation of state, which is W equal to P by rho, the particle horizon eta can be defined as this di by df dt by at, and it can be integrated in this particular form. The important thing is that if strong energy condition is satisfied, which means that the universe is just filled with dust, radiation, massless scalar field, and so on, then the co-moving Hubble radius, which is given by ah to the power -1, it increases during expansion, and the Hubble sphere grows if we have dust, radiation, and massless scalar. Now, if the Hubble sphere grows, that immediately poses a problem to us, that how do we explain the almost perfect isotropic nature of CMB in a standard Big Bang model if the Hubble sphere is always growing? And this is what essentially is a horizon problem. If we are just concerned with dust, radiation, and massless scalar, then it turns out that we cannot explain why there are almost 10,000 disconnected patches in CMB. The CMB almost looks very uniform at even like at very, very large scales. Then remember, like at any 2 points which are even more than a degree apart, if you look at CMB, even they will not be in causal contact. Forget about like even the very largest scales, 2 points which are just more than a degree apart in the sky, even they will not be in the causal contact if the universe was filled just with dust, radiation, or something like massless scalar from the very beginning of the universe. The horizon problem essentially is that if the Hubble sphere the resolution of the horizon problem is that if the Hubble sphere actually decreases sometime during the expansion in the early universe, then there can be a way to explain the causal connection between different points in CMB. Otherwise, if the Hubble sphere was always increasing, as we can see from this equation and from the equation of state, then there is no way we can explain like why CMB looks so uniform at different parts of the sky. But this also means from this equation that we must violate the strong energy condition, which means from Raychaudhuri equation that at some point the universe was actually having an accelerated expansion. The universe was actually having some sort of an effective repulsive gravity. The things were not just coming together, the things were also pulled apart. And this is the Hubble horizon problem forces us to violate strong energy condition at some point in the early universe. And this is where is the seed or the necessity of inflation comes in. Inflation is essentially the phenomena where the strong energy condition was violated. And from Raychaudhuri equation, we understand that there was an accelerated expansion in the very beginning of the universe. So what is inflation? So roughly speaking, inflation is a phase of accelerated expansion in the early universe where strong energy condition is violated. This is the most popular paradigm to explain observations by introducing scalar field potentials. We still haven't pinpointed what is that potential of inflation, but thanks to precision cosmology experiments, we have ruled out various potentials which were very natural just a decade ago. In inflation, we are going to take a field which is called an inflaton field, where the energy density will be given by phi dot square by 2, where dot is with respect to the proper time, plus u, which is the potential of the field, and the pressure will be phi dot square by 2 minus u. The conservation law, which we saw earlier, if you plug in that rho and p, it leads to this Klein-Gordon equation, which you can also independently derive from the Lagrangian of the inflaton field. This is essentially a potential of an inflaton. This should be u phi plotted against phi, in which an inflaton starting from top of the potential rolls down, and then it will reheat here and generate the standard Big Bang model of the particles, Big Bang nucleosynthesis, and so on. There are many question marks even here. Like people like Stephen Hawking, for example, have pursued for a very long time. How did the inflaton started on top here? And there has been very beautiful work, even in loop quantum cosmology, where Ashtaker and David Sloan had earlier shown that starting from the big bounce, the field can be pushed up, and then it can roll down and so on. So loop quantum, I won't go into details here because there is not much enough time to explain the initial conditions for the inflaton, but I'll mention it briefly later. Inflation is past incomplete, even if the equation of state here is very close to -1. What happens is that inflaton starts from here and starts moving down. It goes through a slow roll inflation, which means that kinetic energy is much smaller than the potential energy. W is -1. And going back to how the scale factor changes with time, it goes through an almost exponential expansion, which is measured in number of E foldings. And we roughly need 65 E foldings to explain the observation. Very important theorem by Berde, Guth, and Valenkin shows that inflation is past incomplete. So even if the inflation is happening, it's almost de Sitter revolution. It doesn't mean that the Big Bang singularity, it doesn't mean that the singularities actually resolved. So we still have to answer this question, and I'll show you like how loop quantum cosmology tries to answer that later on. Now, this will be relevant for us later on in the part B. But what actually happens is that if you didn't had inflation, I'm plotting here the co-moving horizon versus the log of the scale factor, log of the Hubble radius versus the log of the scale factor. And I'm showing different regimes. The phase in which the inflation is going on, and then at some scale factor, the inflation ends. Then at this scale factor, where the reheating has happened, the universe was radiation dominated, and at some point, the radiation cools down, leads to matter, which is actually dust in the cosmological sense. Now, this should be dust. And then the universe is decelerating at a different pace, so that is why the slope changes. Then this is what the behavior of the co-moving horizon looks like. Now, what happens is that the inhomogeneities, which we see actually in the CMB, they are arising from certain quantum fluctuations of the inflaton. These quantum fluctuations, these have the physical wavelength, which is shown by this red line here. These move out from this co-moving Hubble radius, and then they re-enter, they freeze once they are outside the horizon, and then they re-enter in the matter-dominated phase or in the radiation-dominated phase, and so on. In the Fourier space, when you look at the power spectrum of these primordial perturbations which are generated here, and then they are imprinted here in the cosmic microwave background, then they turn out to be having almost scale invariant spectrum, which means that they are almost, the spectrum is independent of the wave number of the Fourier modes in the observational regime. Now, inflationary cosmologists and astronomers, they have studied these inflationary models very, very extensively. The goal of loop quantum cosmology is twofold. First, to see like what happens beyond this, before this inflation started. What was the behavior of this co-moving horizon? And second, can there be quantum gravity effects here or somewhere here in the pre-inflationary regime, which can be encoded on these primordial perturbations, and can we see those quantum gravity effects in cosmic microwave background now? So that is the main goal of the practitioners of loop quantum cosmology. So what is this ultimate? So now with this brief cosmological preliminaries, I'm going to move to the strategy. What is the main strategy which we try to follow? This is the ideal strategy. This is not probably the most practical strategy in all the papers, but this is what, when we started these works in Penn State almost 18 years ago, this was the strategy which we laid down that we should be following. The idea is that we quantize the classical system. Take a classical system, you quantize it as rigorously as possible, which means that find the physical Hilbert space, which means find the inner product, Dirac observables, physical states, and so on. Then consider certain physical initial states, such that in the GR epoch. Why in the GR epoch? Because the problem of finding the initial state of the universe is much, much harder. And there have been works on that in loop quantum cosmology. I won't be going into that in detail, but there have been work both on trying to connect it with tunneling wave function as well as with the no boundary wave function and so on, and many other works. But the idea is more pragmatic, that we know we live in GR epoch. So let's take a state now as our physical initial state and evolve that state using the quantum Hamiltonian constraint, which we'll obtain from the first bullet point, and evolve it backward towards the Big Bang, and then see let's see what happens. Almost on all occasions, the model will not be exactly solvable. One will need to do a lot of heavy numerical simulations, but fortunately, at least in one loop quantum cosmology case, we were able to find an exactly solvable model, and we were able to answer all the questions analytically. Once you have evolved the states, we have to compute the expectation values of observables and their fluctuations. Then you can compare with the classical trajectory. And then you can obtain the departures between GR and your quantum model. This is for LQC, but you can have your own favorite quantization of a quantum cosmological model, and then you can understand the same things. Then the goal is to make precise statements about how singularity resolution occurs, which means what is the behavior of energy density. If you have an isotropic model, then you will have shear, what is the behavior of shear scalar, what happens to curvature invariance, and so on. And after making those statements, then one should try to extract robust phenomenological predictions, say for inflationary model or CMB, and so on. This is an ideal strategy. There are certain shortcuts which have been shown to be very robust. For example, like there is an effective space-time description which has been captured in last 20 years in loop quantum cosmology, which is used very heavily for these phenomenological predictions. Okay, so let's go ahead. But Jurek, are there any questions so far?
Are there any questions? Yes, there are some questions. Thank you.
Yeah, I have a very fundamental question actually, but how can we actually regard certain conditions at the initial state to be physical? So what is the proper criteria? Because usually in GR, no matter what kind of initial state that we choose, we somehow will be eventually facing the singularity. So what will be the proper initial states that we can put into the theory, and then it gives the regular kind of evolutions in the quantum stage?
Thank you. Thank you so much. This is a very good question. And like we spent lots of years trying to answer that question. So initially in 2004, when we started that work, and it took 2 years for us to like really go through all the rigorously, like all when the APS paper first came out, we were focusing on the Gaussian states, which were peaked on the classical trajectories for a macroscopic universe at the late times. But this question kept bothering some of us for a very long time. And I will try to answer this question later on in the talk, where we don't even just take the Gaussian state, but highly squeezed states, very, very quantum states. And we have done simulations with those states with full quantum Hamiltonian constraint. And then again, we show that the singularity is as robustly resolved as with Gaussian states. Also, like there is an exactly solvable model in loop quantum cosmology, which shows the singularity resolution occurs for a dense subspace of the physical Hilbert space. So yes, that question, these answers do not answer your fundamental question of if I take an arbitrary potential in GR, and if I take an arbitrary initial state, can loop quantum cosmology give me the answer that the singularity is fully resolved? No one knows that answer today. But the evidence is, the circumstantial evidence is very strong that for any model which we have studied so far, which are many, including anisotropic models, and for any initial state which we have considered so far, we have always seen singularity resolution in loop quantum cosmology. So let us go ahead. Okay, I hope like this answers partly your question. Okay, let's go ahead.
There is one more question.
Yeah, I have a question before you mentioned that the involution indicates the variation of the strong energy condition. Can you give a little bit more detailed discussion? Because I cannot see the relationship between them.
I'm sorry, like if someone can repeat the question, I couldn't fully hear properly.
Okay. I mean, before you mentioned that the evolution indicates the variation of the strong energy condition.
Okay.
Yeah.
Okay. No. So the answer is, so if I understand the question correctly, is there a violation of energy conditions in loop quantum cosmology? No. There is no violation of.
I mean, for the inflation.
Yes.
Yeah.
For inflation, the strong energy condition is violated, but the null energy condition is not violated. That is why inflation is still passed incomplete.
But I just don't understand why the strong energy condition is violated in the evolution.
That is easy to see, because like if you plug in, let me go to the inflationary slide. Like if you plug in If you take this rho and p, and if you look at the equation of state, which is the ratio of p divided by rho, then for a positive potential, if phi dot square is less than u, you can see that w will be less than -1/3. It's just a small calculation. But like, I have not shown that calculation, but my student is sitting there in the red t-shirt in the middle, like he's an expert on inflationary models. He can easily explain to you.
Okay, thank you.
Okay. Okay, so let's go ahead.
Yeah, let's continue.
Okay, so let's take a massless scalar field. So I'm going to go to a specific model now. So homogeneous and isotropic universe with a massless scalar field. And due to the underlying symmetries of the homogeneity and isotropy, the spatial diffeomorphism constraint is satisfied. And I'm assuming here that every one of you have attended Christina Giesel's talk and Abhay Ashtaker's lectures. So I'm not going to explain these things, many of these things. I'm going to build up on their lectures and just speed up on some of the things. So the spatial diffeomorphism constraint is satisfied, and the only non-trivial constraint is the Hamiltonian constraint. The matter Hamiltonian H phi can be written as p phi square by 2v, where v is the volume of the physical volume of the universe, which is given by the fiducial volume times a cube. And using this Hamiltonian, you can look at the Hamilton's equations, which will give you p phi equal to constant and phi going as log of v. Okay, like this v should be capital V, and rho going as a to the power -6. There are two solutions in this from these Hamilton's equations in GR. If you plot volume of the universe versus the time, which is phi, which acts like a clock, there are two solutions. An expanding universe, which goes like this, and a contracting universe, which goes like this. These two solutions, they are disjoint. They are both singular. If you are in an expanding universe and if you look backwards, there is a Big Bang. If you are in a contracting universe and if you go forward in time, then there is a big crunch singularity here. So there is a Big Bang here and big crunch here. They are disjoint solutions. So let's talk about Wheeler-DeWitt quantization attempt to quantize this system. So we are going to use the same strategy, but we're trying to quantize a system that quantize the geometry and matter for a homogeneous universe. Why? Because we have only finite number of degrees of freedom, and the system can be treated quantum mechanically. And the early attempts were based on these works by Misner, Wheeler, and DeWitt. The basic variables we can write in terms of the Misner kind of variables, the volume and the momentum of volume, which goes as v dot, and phi and p phi, which goes as matter. We can make them as operators in the Hilbert space. So v hat and acts on wave function psi of the universe, which depends on the volume, with time or clock phi, which is multiplicative, and its conjugate acting as a differential operator. The Hamiltonian, again, I'm not worrying about the factor ordering here. So it will be something like this, the gravitational part acting on psi and the matter part acting on psi. And for this massless scalar model, the Hamiltonian constraint is very simple. It looks like del square by del alpha square psi equal to del square by del phi square acting on psi, where alpha is log of v. You can write down Dirac observables. You can write down the inner product. It's a very beautiful, simple theory. And to extract departures from GR, you can consider a semi-classical state, a Gaussian state, at late times, let us say today, in the present epoch, and evolve it backward towards the Big Bang. And you can ask the question, if I do this numerical simulation, am I going to get, if I start a state here and if I evolve it towards the Big Bang, am I going to get a singularity resolution or not? So you can do this exercise, and this is the plot from a simulation which we did. What we find is that the Wheeler-DeWitt states, they will just follow the classical trajectory. If you will take the state at large macroscopic universe, evolve it backwards, it will just go into the Big Bang. The singularity is not resolved. You can also take some different states, squeeze states, or very, very non-classical quantum states. Even then, the singularity is not resolved. And you can ask the question, what went wrong? What went wrong is that even though we were doing this Wheeler-DeWitt quantization, see, like we still have these differential operators everywhere. The underlying space is still very different. It's a differentiable manifold. There was no quantum geometry in it. That's the first thing which went wrong. And there was no quantum geometry because we are not deriving this from any full theory of quantum gravity. This was just an ad hoc quantization of certain gravitational phase space variables just using quantum mechanics. The properties of space-time were exactly the same as in the classical theory. There were quantum effects, but the quantum effects were just H bar effects. There was no GH bar effect, which was there in this Wheeler-DeWitt theory. And we know like the H bar effects really they are absolutely limitful. They are completely limited to resolve the singularity. So there was really no Planck scale effects which could have been captured using Wheeler-DeWitt quantization. So Wheeler-DeWitt quantization was unsuccessful, but then we can go towards the loop quantization and see what happens. So again, a very brief summary, like due to the symmetries of the isotropic and homogeneous spacetime, the Archteger-Barbero connection and the triad, they can be written in this simplified symmetry-reduced form, where the V naught is the fiducial volume, this E with a dot and omega with a dot. These are the fiducial triads and co-triads which are compatible with the fiducial metric. The Archteger connection and the triad, they are completely captured by this C's and P's now, which satisfy this Poisson bracket, C comma P equal to 8 pi G gamma by 3, where this gamma is the Barbero-Emirzi parameter. And I'm going to fix this value as 0.2375 using black hole thermodynamics in loop quantum gravity throughout the talk. How are these C's and P related to metric variables? This P, this is a triad component, is related to the scale factor using this equation, where the modulus tells us about the orientation of the triad. And again, like later on, I'm going to fix those in orientation to be positive. And only in GR, the connection is given as A dot. And this comes from the Hamilton's equation. And I urge students to be very careful when using these two equations. The first equation is always true, but the second equation is only true in GR, because this comes from the classical Hamilton's equation. In loop quantum cosmology, this equation is not true. This equation becomes much more complicated and becomes a trigonometric function, which is now equal to A dot. Now we promote these classical phase space variables and the classical Hamiltonian constraint to the quantum operator analogs, and we actually construct the holonomies of the connection along edges and the fluxes of the triads along the two surfaces. And due to the homogeneity, the fluxes are just proportional to the triad. The holonomies of the symmetry-reduced connection, they look something like this, with the fiducial length mu, which is being used here to define the holonomies. I denotes the unit 2 by 2 matrix, and tau denotes the polyspin matrix. Tau is proportional to the polyspin matrix, where sigma k is a polyspin matrix. So basically, these holonomies play a very fundamental role, and they are captured by these functions, n mu. Since this mu is an arbitrary function, can take arbitrary values, this n mu is an almost periodic function of the connection C. And because of this, there exists a unique kinematical expression, a unique kinematical representation of the algebra generated by these functions, which was shown by Archteger and Campilia, and Engelhennisch and Thiemann in 2016. And this is parallel to the unique irreducible representation of the holonomy flux algebra in full loop quantum gravity shown by the Loss theorem and Fleischstadt in 2009. The gravitational sector, once you quantize this model, is given by L2R Bohr d mu Bohr. This is a kinematical Hilbert space in loop quantum cosmology, and it is fundamentally different from the Wheeler-DeWitt theory. And one can show that the von Neumann theorem is actually bypassed when one has this kinematical Hilbert space. The action of operators and on this psi is through translation, and where this z is constant. And similarly, the triads act on this wave function through a simple multiplication. Since we don't have fermions in this theory, then the absence of the fermions, the change of the orientations will be a large gauge transformation. So we generally take the symmetric state, which satisfies psi mu equal to psi of minus mu. Using these holonomies, we can then focus on the Hamiltonian constraint. And in the Hamiltonian constraint, one of the main objects is what you would have heard about in Christina's lectures, is this FAB, which is the field strength of the Archteger connection, field strength of the holonomies of the Archteger connection, which is given by this expression up here, in which the denominator here, area of the sphere, denotes the area of a square placket, which and this H square box is the particular structure of the holonomy operators, with this mu bar now, which denotes the edge length of this placket. Due to the underlying quantum geometry, it turns out that one cannot take this area to be 0, that limit does not exist, and one has to shrink this area to the minimum non-zero eigenvalue of the area operator in loop quantum gravity. We are going to denote this minimum value by delta of LP square, where delta is 4 square root 3 pi gamma. Now, in the very early attempts of loop quantum cosmology, like in the, for example, the Ashtaker-Boyewald-Lewandowski results or early results which Boyewald had, this area was taken to be constant. And one of the realizations in 2006 was that one has to consider the physical area of this loop, because we are actually looking at an expanding or contracting universe. Then it only makes sense to take the physical area of the loop. And if you take the physical area of the loop, which is given by mu bar square times this triad, then it turns out that mu bar square has this particular relationship with the triad. The drawback of this is that the action of n mu now on the triad eigenstates is not a simple translation. It becomes much more complicated, and therefore it becomes much more meaningful to do a canonical transformation to new variables, which I'm going to denote by b and v, which are defined by this b defined by c to the power square root of b, and v small v, which is defined as this. In terms of this b and v variables.
Param?
Yes.
10 minutes left.
Okay. So in terms of this b and v variables, the action becomes very simple, that this exponential of I lambda b is given by nu minus 2 lambda, and v acting on nu just gives you this multiplication for the new eigenvalues of this new operator. The quantum Hamiltonian constraint can be written in this particular form. It similarly takes the form of del square phi acting on psi equal to minus theta acting on psi, where theta is a positive definite second order difference operator. So the main thing which one captures so far from this quantization of a simple model is there is a quantum difference equation which results from quantum geometry, and one can actually also show that this results in a Wheeler-DeWitt differential equation at large volumes. Then one can develop this theory as the Klein-Gordon theory. One can focus on the positive frequency subspace of this theory. One can look at the Dirac observables, which are the volume of the universe at a given time and the momentum of the field at a given time. And one can figure out the expectation values of, or one can find out the eigenvalues of these Dirac observables. One can also easily find out the inner product. So one has a very rigorous theory, rigorous quantum theory, which one can write down for this very simple model. If you evolve now this theory and you take a physical state at late times, and let us say at late times in here, somewhere at the large macroscopic universe. Here I'm plotting the volume of the universe versus the wave function and the scalar field phi. And if you evolve it backwards towards the Big Bang, then one finds that it doesn't go into the Big Bang anymore, but actually it just bounces once it reaches some energy density, which is given by rho max equal to 0.41 rho Planck. It just bounces and it actually latches down to the other trajectory, which was of the contracting universe. So let me show this plot again. So this is the similar plot which I was showing earlier for the classical universe. Now those red lines are given by the blue lines, volume of the universe plotted versus the time phi. This is the loop quantum cosmology expectation values versus the classical curve. And if you start from some universe here, instead of the universe going into the Big Bang here, the universe actually bounces and has a big bounce and goes into the contracting branch on this side. The singularity is recovered if you take the area gap, which played an important role. If you shrink that area gap back to zero, if you just put it back to zero, these states will just go into the singularity again. You can also figure out the probability of the bounce using the consistent quantum probabilities. And it turns out that this particular model, the probability of bounce is actually zero, and the probability of Big Bang is, the probability of bounce is actually unity, and the probability of Big Bang is actually zero. And the robustness of the bounce has been shown in many examples. This is for the massless scalar field in spatially flat, but in last decade or so, many groups all around the world have shown it in many cases. First of all, there was an exactly solvable model which was beyond numerical simulations, which showed that for all states in the physical Hilbert space, there is a non-zero minimum volume, which means there is a bounce. Then in the presence of the spatial curvature, both for the closed and open models, the bounce was shown. Then the singularity resolution was shown for Bianchi models, in particular for Bianchi 1, Bianchi 2, and Bianchi 9 models, for including a negative cosmological constant, positive cosmological constant, a phi-square inflationary potential. Unfortunately, there is this beautiful work, which is still a preprint form, which we never posted on archive also. And later on, like with Christina Giesel and Boffey, like we did for two scalar fields, like with one test scalar field and inflaton. For very extreme states, which are not even classical, and very non-Gaussian states and highly squeezed states, we showed this. And similarly for the radiation. Now, an important thing is the effective dynamics here. The effective dynamics, like, so Jurek, how much time do I have? 5 minutes or 2 minutes or?
5 minutes.
Okay, so I think like I can still go for a couple of more slides. It turns out that for suitably chosen coherent states, you can follow a beautiful description of quantum mechanics, which is called as a geometric formulation of quantum mechanics. And one can actually write down an effective Hamiltonian, which beautifully captures the underlying quantum dynamics, which I showed you. And this work was done by Victor Tavares in his PhD thesis, and he won I think, a Wheeler Prize based on his thesis, primarily probably because of this work. And he showed that there is an effective Hamiltonian one can write. And this effective Hamiltonian, if you take the vanishing of the Hamiltonian constraint, it gives you an equation which is like this. And this has to be contrasted with the classical Hamiltonian constraint. But if you look at I showed you like starting from the classical Hamiltonian, like how you get the Hamilton's equation, the Friedmann equation, and so on. If you do the same exercise for the effective Hamiltonian constraint, you get a modified Friedmann equation. Instead of h squared equal to 8 pi g by rho, you get h squared equal to 8 pi g by rho, 1 minus rho by rho max, and with rho max equal to 3 by 8 pi g gamma square by lambda square. Now you can see when rho becomes equal to rho max, then the Hubble becomes 0. And when rho becomes greater than rho max by 2, one can show that the time derivative of the Hubble will become 0. And in that case, when rho is greater than rho max by 2, the universe actually becomes super inflationary in the sense that it has extreme quantum gravitational induced repulsion. So this idea which we have from GR, that as you keep going towards Big Bang, the gravity remains attractive. And even if you have inflation, the strong energy condition is violated. Like what turns out is that there is no energy condition violation here. This is all coming from pure quantum geometric effects. Translated now in the matter part up here, the equation itself changes such that when you reach energy densities greater than rho max by 2, the universe is actually the gravity is very, very repulsive. And at rho equal to rho max, the evolution just pauses for a moment, and the gravity causes the universe to bounce back. This rho max is exactly the same as we found numerically earlier, and which we find in exactly solvable models. The expression is the same, and the number is the same. And I'm showing you here the plot of a model, which is K equal to 1 FLRW model of loop quantum cosmology, effective dynamics, and the classical theory. The red points are loop quantum cosmology. The classical theory is the green line. And the blue line, actually, you cannot even see because it's lying exactly at the red line all the time. And this is for the K equal to 1 model, which goes through many cycles of evading Big Bang and Big Crunch and so on, goes through cycles and cycles again and again. And in this simulation, we are just capturing 3 cycles out of tens of thousands of cycles in which we did the simulations with Abhi Ashtekar and Tomasz Pawlowski and Kevin Wendersloot, and the Warsaw group also did a beautiful work on the mathematical aspects. The interesting thing here in this picture is that the loop quantum cosmology not only avoids the Big Bang problem, but also accurately predicts where will the recollapse of the universe will happen at the classical stage. So it's not only like giving the right answer at the ultraviolet limit, but also in the infrared limit. And you can see that the effective description is beautifully matching the quantum description here. So some questions. Is quantum bounce a generic feature of the states in the theory? This was one of the questions which was pointed to earlier. And the answer is yes. The bounce happens for all the states in the physical Hilbert space, for the spatially flat isotropic model. For other models, we do not have an exactly solvable model, but we have done probably millions of numerical simulations now using high performance computing for different kinds of models. And the answer has been always yes. What is the state of the universe on the other side? Is it a quantum foam or a classical space-time? A macroscopic universe, such as ours, bounces from a macroscopic universe similar to ours. So if you start from a macroscopic universe, You evolve it through the bounds, you will get a macroscopic universe like ours. If you start from a quantum universe, you will end up with a quantum universe. The space-time fluctuations are severely constrained on both sides of the bounds. There was a debate long time ago, maybe 15 years ago, that as you will reach bounds, there will be space-time fluctuations and they will destroy the bound. It turns out to be opposite. Space-time fluctuations actually help repulsiveness of gravity. Then the question is, what happens to the quantization ambiguities? We just talked about one particular factor ordering, talked about one particular regularization. Do they affect the results? It turns out that even at a very theoretical qualitative level, you can rule out many models very easily by just looking at the strong energy condition and so on, which will come from the effective dynamics. And this is the work which Alex Corici and I did. These are the consistency conditions that the theory should not depend on the fiducial cell, theory should not depend on should give the right IR and UV limit. And this was also in the APS model earlier. Recently, in last few years, there have been new regularizations which have been studied on loop quantum cosmology. There is a bounce, but then it turns out that the bounce is asymmetric for the massless scalar field, and I will try to show you later in the talk. But I'm not sure, Jurek, how much time I have right now.
Yes, so can we stop at this point?
Okay. And after how many minutes we rejoin?
10 minutes.
Okay.
You just have to wait only 10 minutes and then you can go on.
Okay, thank you.
Are there other questions? Okay.
Yeah, so I'm still confused about this singularity resolutions because in a previous slides you're mentioning about there's some conditions about singularity in the within the notions of having a metric, but once at the stage of states, like a quantum state, how do we say that the singularity has been resolved? Do we follow the trajectory, and with that, can we say that this resolution is similar to like geodesic completeness?
Yes, we can say that, and I do not want to go to those slides, but yes, you can. So, in this, I'm talking in the historical evolution of the subject right now, and in these papers, we started from a coherent state, which was peaked at the large macroscopic universe. And we found that when we looked at the expectation values, which were computed using these Dirac observables, if you look at the expectation values, and these are the expectation values which are shown here in this red one finds that there is a non-zero minimum expectation value of the volume at which the bounce happens. And this was then also showed using the exactly solvable model in terms of the expectation values, that there is a non-zero minimum of the expectation value of the volume. Then you can ask two kinds of questions. One is, well, can we talk about geodesic completeness? I will pause for that for a moment. But I think the bigger fundamental question is, well, you are talking about expectation values, but what about probabilities? Is there a probability of, you have to compute the consistent quantum probability somehow. And then we found that if you compute the consistent quantum probability, then the probability of the bounce to occur in this physical Hilbert space is unity. There is no way, there is no probability that the bounce will not occur. So in that sense, so the singularity resolution in this sense, which was answered. Later on, when we had more faith thanks to all of these works, testing different models, testing effective dynamics, and so on. Later on, when we tested this effective dynamics in all of these models, it has been tested very rigorously. Then using this effective description for arbitrary matter. Now that's an assumption again. For arbitrary matter, we had to make, because we had tested for different models, for different potentials and so on. Because if you see, right, for the massless scalar field, the equation of state is equal to 1. But for the positive cosmological constant, the equation of state is -1. From W equal to 1 to W equal to -1, which is the entire regime of the negative for the null energy condition. Once we tested this, I think it would be fair to make that assumption that the effective dynamics works pretty well. And including also for the Bianchi models where we showed that effective dynamics really works pretty well. So it was a reasonable assumption I think one can make that the effective dynamics works pretty well. If you make that assumption, then one can actually show, and maybe like, I'm not sure like if I'll be able to go to that slide, so I can go to that slide now, if you want. One can actually try to answer this question using geodesic completeness and using the very rigorous analysis of the strength of singularities, that all singularities, all space-like singularities in isotropic homogeneous models, as well as Bianchi 1, Bianchi 2, and Bianchi 9 models, they are all resolved in the effective dynamics of loop quantum cosmology. So you can answer the geodesic completeness question has been answered using effective dynamics. I'm not aware of a work where the geodesic completeness question has been answered using expectation values. Probably that is that's a very good PhD project for some student who is interested here. But using effective dynamics, yes, one can very rigorously prove almost as a theorem that it is geodesically complete, no violation of energy conditions, and all strong curvature singularities are resolved.
I suggest to stop at this point and thank speaker again.